So here we go. This one here had a red ball moving in a straight line like this, and this is the epitome of what we call a glancing collision, where one is going to go up, one's going to go down, it's going to split into a Y. I have good news for you. If you get a scenario like this and you understand some of your math principles, which, guys, we're doing physics, you need to have a good foundation of math, you can solve this fairly simply using the cosine law. Okay, let me re-diagram what we did last day just on a new slide here. We had one ball that was going in like this. I'll use black for it. Then the black one, which one went up again? Okay, that one went up. So the black one went up like this, whereas the one that was stationary went down like this instead. Okay. Now, because of the fact that the one was stationary when it began with, I only have three vectors to deal with. I have the incoming, the outgoing, and the second outgoing. I can actually pick these up tip to tail method, which I'm hoping you guys experienced last year in Physics 20, and you can make it look something like this. Here's the original incoming vector. Then one went up like this. That was this one here. I'll just call it A, just to make sure it's clear as to which one was which. One's going to go down like this. That was B. And then the original one here would have been C. And so I made myself a triangle. Okay. I can label a few more things. For example, I can find the momentum of C, because I believe I was given C's momentum values to begin with. They were 1.2 multiplied by 17.1. So this is whatever 1.2 multiplied by 17.1 is. And the other momentum value I knew, I think, was A. Yeah, because this one went 1.2 and 13.5 when it went up on the side. So this is going to have a momentum of 1.2 at 13.5. So I'm just going to calculate those values real quick so that they're written down again. 1.2 times 13.5 gives a momentum here of 16.2 kilogram meters per second. Did I do that right? It's 13.5? Yeah. And then 1.2 times 17.1 gives me a momentum value on this long side right here. I've got 20.25 kilogram meters per second. And what we're really looking for is we're going to be looking for side B over here. However, I was given an angle. The angle was 23 degrees. So this angle right here being 23.0 degrees gives us enough information if you know how to use the cosine law. I think this is more or less where I got to last day, except I was starting to run out of time. So quick math reminder. I guess I chose A, B, and C as the values I have right here. It really doesn't matter what letters I use. As long as you know how to use the cosine law, it would look something like this. Normally it's C squared equals A squared plus B squared. But with the letters I chose, it should probably be something like this. B squared equals A squared plus C squared minus 2AC cosine of B, which is the angle in between them. That would be how this particular cosine law would work, based on me choosing these sides to be A, B, and C. You want to change the letters around, go for it.
And that solves for the impulse, right?
That'll solve for the impulse on this side. Yeah, good question, right? What we're going to do is we're going to solve for the impulse on this side, but that's not necessarily what we need. We need the velocity. So if I want to calculate that velocity, I'll have to divide by its mass. But we'll get to that. Yeah. Impulse is the change of momentum, yeah.
Oh, since it said 0 to 2.
Yeah, because it started at nothing, right? And it's moved, right? So its impulse is its change of momentum. We're talking the same thing. Good questions, guys. Okay, so I'll try plugging in some numbers. Again, I did this last day. This is going to involve me taking, let's see, 16.2, square it. We're going to add 20.25. We'll square it. We'll minus 2, 16.2, 20.25, and the cosine, I'll just write it down here, of 23 degrees. And I think last day before I was running out of time, I pointed out a couple thoughts. One, don't forget to square root, because this is what B squared is equivalent to, and make sure you're in degrees, not radians, because that would really bugger things up. So Open offer here. If any of you are really fuzzy on some of the math principles that we're going to talk about today for trigonometry, please don't hesitate to ask for help from me. Because this is one of those courses that kind of assumes that you have background information. So if I'm hoping that everyone here has done at least a Math 20 course. I mean, it can be 20-2, it doesn't have to be 20-1, but it's going to pull on your math skills for sure. So I got a value here. Let me know if anybody else got something different. I got 8.28 after I square rooted. Anybody else try it and get that? Nobody else did. 16.2 squared plus 20.25 squared minus 2, 16.2, 20.25 cosine 23. Yeah, I got 8.28. What did you guys get? What did we get last day when we did it? I forget. 8.56 I got last day? I typed something in wrong? Let me just check my math. 1.2 times 13.5 is 16.2. Yeah. 1.2 times 17.1 is, oh, sheesh, I'm dyslexic. This was not 20.25. This was 20.52. Sorry to anybody I might have messed up here. That was 20.52. Which makes that 20.52, which makes that 20.52. Sorry, my bad. Okay, let's try that again. 20.52, 20.52. Now square root it. How about 8.456? 8.456? Okay, I'm getting some nods finally. Okay. So after doing the cosine law, I got 8.4566, etc. That would be, as we've kind of already mentioned, that is our impulse or our change of momentum, which is great. If I go back to my picture over here, I can now label this side here. I'll even do it in a new color. This side's vector sum was the 8.456 kilogram meters per second, but that is a momentum, a change in momentum value. We wanted velocity. So to calculate its velocity, you know how momentum is mass times velocity, divide by mass. So if I divide this thing by its mass, which was, what, 2.31? I got 3.66. And I think this is where I ran out of time the other day. Does that match up with what we were doing before? Get some nuts here. Does anybody have any questions on that part? Because we're not done. We have an issue. If I were to go back up to this drawing I've got right here, I now know that this red vector right here, the downwards vector, I know how fast it's traveling in terms of speed. It's going 3.66 meters per second. But with it being a vector, I need a direction as well. So we need to calculate kind of this angle right here. You guys see that? This angle right here, we need to know because it's going east something south. To do this, we need to know the sine law from math. Again, something you ideally did in Math 20. In order to calculate this angle right here, if I can kind of draw in this diagram here, can you guys see how this line right here is this one I'm drawing in right here? That's the same vector I'm discussing. Which means that I need to try to find a way to calculate, if I could kind of like draw like a horizon right here, this angle right there. That angle is not even inside of the triangle. That is an exterior angle. It's not even a full angle. It's like a partial angle to the triangle. That being said, if you know your trig principles, one of the angles inside the triangle is this angle right here. Do you guys know which one it is? This one down here. There's a math property known as alternate interior angles that maybe you've come across at some point before. The basic idea is that this line right here, which went straight across, and this line right here are supposed to be parallel to each other. It means that this angle right here, which why don't I just label it as, I don't know, x, I guess, for right now, and this angle right here, they're the same as each other. So you guys have seen that before? Getting some nods. Okay. Like I said, if I ever lose you on the math part of things, can you talk to me? Because unfortunately, math is just like it's a prerequisite for physics. So long story short, we need to find this angle right here. To do that, I would use the sine law. I would say that, like, say sine of A over A, this side right here, should be equivalent to this angle here and this side here we just calculated. So it might look something like this. I'll just need to make a new one here. The sine law looks like this, like sine of A over A equals sine of B over B equals sine of C over C. That's probably how you saw the sine law. I just need to figure out which ones I want to use. I don't actually have to use all of A, B, and C. I just need to pick the ones I want. So in terms of stuff I know, let me go back here. I know side A, and I'm looking for the angle across from it. So that one I can use. And if I pick a new color here, I know this one right here across from B. So I'm just going to use the A's and B's. I'm going to skip C because I don't even know what this angle C is over here. So let's fill in some numbers here. Sine A, I think that's what I'm looking for. I want to know that angle. I'm going to divide it by the value across from it. So if this is like the angle A, side A is over here, it was 16.2. So I'll put a 16.2 there. And then sine of B, I believe I know this angle. It was 23 degrees. And the value across from it, I just solved for. But which one am I using? 8.4566 or the 3.66, right? Which value should this side be here? Should it be the momentum side or the velocity amount? Yeah. And the reason why it should be momentum is that this one right here was in momentum. So if this side I'm solving for here is in momentum, then this side over here better also be momentum. So I'm going to use the 8.456 value. And I'm going to try to use all of its decimals. So like I still have it in front of me here. It was 8.4566, etc. So now I have to solve for what angle A is. Multiply this up to the other side. And you guys know how to inverse sine something? Again, if I'm losing you here, talk to me later, please. So sine of 23 divide by that number multiplied by 16.2. And if I inverse sine that, I calculated this. So this is angle A. I got 48.46 degrees. So I can finally give you an ultimate answer to this question. So I'm going to try to go back to my previous slide here. This angle right here was 48.5 degrees, let's call it. It means that this angle here is also 48.5 degrees, which means that this angle up here that I was originally looking for, if I can kind of draw an arrow in there, this is my 48.5 degrees. So my final answer is this thing was traveling 3.66 meters per second. It was going mostly east, and it was going 48.5 degrees towards the south. You guys seen that kind of notation there? It's going mostly east, but it's offset by 49 degrees south. That's tough, eh? That is not an easy question by any means. Like, I'm doing my best. I know I'm writing on my little board here, but like I've got notation stuff like everywhere. You know, in terms of my picture, I've got some sine law work going on over here, some sine law down here, some cosine law up here. I've got, where was I? There it was. Right. Does that make sense? So it was mostly going east. This would be east going this way, but it's been offset by that angle towards the south. So, yeah, you could do it. You could do a different way as well. You could do 48.5 degrees south of east. Have you guys seen that notation? That works too. Like they're both the same thing. So the way this one works is it goes east, number south. So the way that works is go east, then the number tells you how far to tilt, and you're either going to tilt up towards the north or down towards the south. Here, let me show you this in case you haven't seen this. If I were to give you west 20 degrees north, it means draw an arrow going west, then tip it up 20 degrees towards the north. That's the way you're going. If I gave you north 20 degrees west, it means start going north, tip it to the west by 20 degrees. This can be written the exact same way as 20 degrees west of north. You guys okay with that? Okay. This is one of the hard things because I didn't teach you guys last year. I'm trying to figure out like what you've seen before. So come find me if you need help. So okay, let's try one more example here. That one's actually, for as much work as it is, that's actually still an easy one because this one here is the beast. This one sucks. Okay, and let me try to show you why. Because we have two objects in motion, we cannot use trigonometry to solve anymore. This is the final type of collision you're going to get, and I want to do an activity tomorrow to give you like a hands-on scenario. We're going to videotape it. We're going to do a collision of a couple pool balls running into each other. We're going to videotape it frame by frame and hopefully watch them like come in, collide, and bounce out. And what we're hoping to be able to do is solve a question just like this. Here's the problem, though, as to why we cannot use trigonometry. If I were to pick up all the vectors, I need one going up. That would be like, say, this one here. I would then need one going down. That could be like, say, this one right here. I would need another one going up like this. That could be, let's say, this one going right here. And I could have a final one right here coming down in this direction, going there. I could make myself some sort of vector thing here. The problem is it's not a triangle. And if it's not a triangle, I cannot use trigonometry. Because like literally trigonometry is based on something with three sides. So it kind of stinks. Which means we need a lot of room for this one. Because we have to break things up into its x and y coordinates. And do this like the long way. I'm hoping this is again something familiar to what you did previously. But what I'm going to do is I'm going to make a triangle right here in black. And I'm going to calculate the momentum in the y direction. And I'm also going to calculate the momentum in the x direction. And then I'm going to do that for every single triangle here. In red, I am going to make a triangle out of this right here and calculate the momentum in the y direction and momentum in the x direction. And I'm also going to do that over here. Oh, let's pick a new color. I'm going to draw a triangle here. And I'm going to calculate the momentum in the y and the momentum in the x. And all of that is to help me finally figure out what this one right here is going to do, which again, what color haven't I used? Let's use yellow, I guess. It needs to have a momentum in the y and a momentum in the x. And we even need to have an angle here as well. This is going to be a lot of work. So I'm going to have to flip back and forth between slides. So let me know if like I lose you as I flip back and forth. I'm going to start with my black triangle on the next slide. So the black triangle, and you may even want to do it with like A's, B's, C's, and D's. But one of my triangles looks something like this. The angle in the corner was 30. And it was traveling, let's see, it was 1.2 traveling at 10, it looks like. 1.2 traveling at 10. So this would be 1.2 by 10. And I want to calculate its momentum in the y and its momentum in the x. Do you guys know like the general rule of thumb as to if you have an angle in this corner here, how to calculate this one and this one based on sine and cosine? The adjacent one is cosine, and the opposite one is sine. So if you wanted to do this exactly, this guy's momentum would be 1.2 times 10 times the cosine of 30. And this one up here would be 1.2 times 10 times the sine of 30. Is that something familiar? Y values are always sine, and cosine values should be, like adjacent should be cosine. Okay. Yeah, that makes sense, right? Like this is the opposite side of this one, so it involves sine. This is the adjacent. So I'm going to calculate these values here, and I'm going to try to store them as like letters. I think just to keep track of things, I'm going to call them like A, B, C, D, and E, because we're going to have like values everywhere here. So 1.2 times 10 times the sine of 30 gives me 6. I guess kilogram meters per second is my unit. Right on the dot. I'm going to call that A from now on. And down here, 1.2 times 10 times the cosine of 30 gives me 10.39, etc. 1.2 times 10 times the cosine of 30 gives me 10.39 kilogram meters per second. And that is my, I'm going to call that B. So if I'm going back to the previous slide, if it's okay for me to flip, I'll come back again. I've now calculated this value as a y component as the letter A, and this one is B. Make sense? Yeah, that's what I'm saying. The hypotenuse was the 1.2 times 10, but then when I break it up into its vector values, doing it by sine gives me this sign, and by cosine gives me this one. Right, so just the 1.2 by 10, I agree though. That is the hypotenuse. I'm breaking it up using trigonometry into its y and x components.
So is that the same thing as just the ratios?
Yeah, I'm kind of like skipping ahead. Like if you want, I can walk back through like sine of theta equals opposite over hypotenuse. The opposite would be this. The hypotenuse would be this. So yeah, it's SOHCAHTOA. Right. Again, if you want, I can do a quick math lesson a little bit later. It's just, okay, let's try another one here. Let's try this red triangle down here now. It's very similar. Okay, so I just need a new one. So red was looking like this, I believe. The angle in the corner was 40. And the hypotenuse was, let's see, 15 and 231. 231 and 15. So this is 231 by 15. So again, that is the hypotenuse, but I need to break it up into, let's call this momentum x, momentum y. Okay. So this one right here is going to be 231 by 15 by cosine of 40, because it's going to be the adjacent side. And this one over here is going to be 231 by 15 by sine of 40, because it's the opposite. So I got these values 26 and change and 22 and change. Anybody else tried it just to make sure I didn't mess up? So I'm going to do this a lot in class, by the way. I think it's always good just to have someone double check the tedious calculations. So did anybody else get those values just to make sure I didn't mistype them? Okay, Philip said yes. Okay. Give me a sec here, because I want to find all of them first, and then we'll talk about how we're going to use them. Okay, so if I can go back, I'm going to label this one then as maybe capital C. You ask a good question. I want to do all of them first. So this is C and D. So I'm going to make C be this one right here. Well, actually, no. Malik, right? What we're eventually going to do is we're going to find the sum of them. For example, A and D and these two right here better net out to like 0. Like however much A and this one are, better equal D and this one. And similarly, B and C better be equivalent to these ones right here. Does that make sense? Like, but we need to have all of them first. So that's why I'm going to move now onto the green triangle next. So if I'm not going too fast. Green triangle time. New page. Green triangle looked like this one. It also needs a momentum in the y direction, momentum in the x direction. There is no faster way, by the way. Unfortunately, this sucks. It's tedious. The angle was 25 degrees. So this is a 25. And this guy is the red one, so that's 120. And it's moving 13.5. So I need a 120 and a 13.5 for this one. So the hypotenuse is 120 by 13.5. So hopefully you're getting the hang of this. This guy is going to be 120 by 13.5 by sine of 25 degrees. And this one will be 120 by 13.5 by cosine 25 degrees. Do you guys remember doing this in like your forces unit last year? You got to break things up into the x and y components. It's tedious. It sucks. Like there's no way around it. The advice I'd give you is you definitely want like meticulous note-taking skills so you can keep track of where your numbers are, because like this will take you a full page probably to solve. So okay, let me pull out some values here so that you get the same thing. 120 by 13.5 by sine 25. Does anybody else get 685, I guess, when you round it? Yes? Okay. And then the bottom one, 120 by 13.5 by cosine 25, gives me 14.68 kilogram meters per second. And again, try to hang on to as much precision on this as you can. So let's call this like letter E, I guess. That's what I'm up to now. And letter F. So E is my y direction, F is x. So E is going to be this side right here. And F is that side here. So I'll go back here in case anyone needs to write these down again. I just want to give you guys some wait time in case anyone's still catching up here. By the way, if you feel like you know where you're going, feel free to hop ahead of me if you want, because maybe some of you kind of know what the next step is. Okay. So here's where we're at. Now we need to solve triangle yellow. Okay. And just because I'm using letters, why don't I just move on here? Let's call this EF. Let's call this G on this side right here. And this side right here can be H. One of the things that you're going to find frustrating about physics going forward is that although you are going to utilize the formulas on the data table, sometimes you just have to like logic out your own formula. And this would be a good example of that. I need to figure out a formula for H and G through logic as to how I'm going to solve those. And maybe for the first one, I should just tell you what it's going to be. Okay. For example, to solve G, here's G's formula. G is going to be equal to A plus E minus D. How the heck did I come up with that? Well, A is how much up momentum we had. So something caused it to go up a little bit. And E also caused it to go up. So that also went up. But D would have had some momentum in a different direction, right? Because D's momentum was actually coming kind of from a different way here. So that's why I'm going to subtract that one there instead. Does that make sense? And then by that value, then G is kind of also going down. I actually realized I totally buggered that up. Hang on one sec here. I did not do that in the right, I had the right letters. I have the wrong signs here. Would you guys agree that G is going down? Okay. Who else is going down along with G though? I screwed it up. It actually isn't D that's going down. It's actually A that's going down. Yeah. This should have been D is going up. D is going up. Right? Because D was going in an up direction. And E is going in an up direction. But A was actually going down. I had the right letters. I had the wrong positive negatives. Well, if you can dig back through your calculator now and find all those values, we should be able to calculate G's net amount here. Right? So I'm going to go back through. I'm going to find them. Let's see. D is 2227. E was 685. And A was 6 right on the dot. So I should be able to calculate this momentum right here. So I'll try to find the exact values in my calculator. 2227 plus 685 minus 6. I have a final value here for G of 23.119 kilogram meters per second. And that's going to be going in a, like, it looks like a south direction, I guess, right? Because that guy's going down. But that is a change in momentum still. I got to get it to velocity at some point still later. So I'm still not even that far yet. Sorry, I'm kind of going to be squished here because I want to keep this slide up here, so I'm so sorry. Sometimes my writing, I like working on this thing, but sometimes I can't be quite as neat as I want to, so I apologize here. I got to find the exact same thing for H. So let's try to write a formula for H. Yeah. Yeah, I got to figure out a way to, like, I need to pick something to be, like, positive and negative, right? So, like, F looks like it's going this way, right? And H is going this way. But this one right here is, they're all going this way, aren't they, right? Yeah. What's up? Yeah, H is the X component on the yellow triangle, right? I think the way this one's going to work is that these guys contributed some momentum that direction. And so, like, if I wanted to write a formula here, it would be that, like, H is going to be equal to B plus C minus F. Does that make logical sense? Like, these two things are contributing some momentum, and then these two things would be equivalent. Maybe here's an even better way of putting it. H and F's momentum should be equivalent to B and C. Maybe if you think of it that way, right? These two momentums right here should be equivalent to these two momentums right here. Okay. Let me make sure I did the other one right here. Based on that logic, A and G should have been equivalent to D and E. I hope I did that right. E is going up, and E is going up, and D is going up. And that should be equivalent to A going down and G going down. Okay. So based on that logic, I got to go back through and find all these values. So this is where it's going to be a little bit messy. I'm sorry, I'm kind of out of room here. B is 10.38 or 10.39. I am adding C, which is 2654. Is your final answer? Okay, give me a second here. I got 1468. So why don't we save some time? Did anybody, what'd you get for that one? Anybody else get that? Sweet. Okay, so maybe I'm going a little too slow, maybe. That happens sometimes. We're still not done. Like, we're still not done. This sucks. Like, it's a ton of work. So here, let me underline these numbers here for anybody who's still trying to catch up here. And in terms of its value, it looks like that is traveling this way, which would be east. If I could give some advice, guys, you are going to get questions like this. You're not going to, like, not every question is this hard, by the way. Not every question is this much work. But you have to be meticulous with how you're going to label things. If you want to go with, like, momentum of A in the X direction or momentum of B in the Y direction, by all means, whatever works for you. There's no one right way of doing it. As long as you get the big picture concept, that's what I care about more. But, like, you are going to have numbers everywhere. Keep track of them somehow. Okay, I'm going to redraw that final triangle now. So the one that's down here, I'm going to redraw that again. So that triangle is now looking like this. It was here, and here, and here. And I now know those values because it was G and H, right? G was on this side, the Y component. H was on this side, the X component. And I know those numbers now because we just solved them. G was 23,119. And H, someone said, was 22,254. Is that right? Yeah, 22. How do I solve for the hypotenuse? Pythagoras' theorem. You guys remember that? So like to solve for your hypotenuse, it's going to be 22.254 squared plus 23.119 squared, all square rooted. That will give you your like momentum. I'll use like an h here on the hypotenuse, which is what we really want. So find those values. Yeah, if you write down like 3 or 4 decimals, that'll work. Do you remember how to store it in your calculator too, though?
Yeah, I was just saying it's hard to keep track of all the names.
It is true, yeah. Yeah. I got, this is my final answer. How many sig digs do we get? Like 2, right? So can you guys see yellow? Is yellow like way too hard to see? I bet you it is. I got this. I got 32.1 after I was done. Yeah? No? Okay. So that's in kilograms meters per second. We still have 2 more problems. The same 2 problems that we had the previous time. I don't actually want a momentum. I want a velocity. So this is actually really easy to solve, though. Just divide by mass, right? So if this is my momentum, if you were to divide it by a mass, that would get you a change in velocity. So what was this one's mass? It was the 231, I think. So if I divide this by 2.31 kilograms, that'll cancel out your kilograms. So I have a velocity of 13.9 meters per second. Last part, still need an angle, which means I need this angle right here. Anybody know how I'm going to calculate this angle right here? Sine law would work. It's actually faster, though, if you use the inverse tangent. We have an opposite, and we have an adjacent. So if that kind of makes sense, this is like the opposite, and this is the adjacent. If you do the tan inverse of your opposite over your adjacent, that'll give you this angle right here. You can use sine law. It just means one of your angles would be 90, that's all. That's the sine law, yeah. And that would work because you do know this side right here is 90. It's just, it's a lot longer work to do sine law. If you inverse tan it, it's the opposite over the adjacent, and that'll get you this angle here. So inverse tan the opposite side over the adjacent side. So inverse tan 23.119 divided by 22.254. And I got an angle of 46 degrees, basically. So that would be, I'm going to write it like this. It was going mostly east, and it was going 46, I have 0.1 degrees south. And we are finally done. And that one sucks. Let's walk through the major concepts of what we did again. And then I'm going to give you guys the last half hour to do some work finally. I'm sorry it took so long. Again, one of the struggles you're going to come across going forward is that it's not just, here's a formula, plug 3 numbers in, solve for the 4th. Those are the easy ones. It's where like you have to use your scientific concepts of conservation momentum and kind of make your own formula. So if I can go back here one more time, I calculated the y and x momentum, the y and x momentum, the y and x momentum of 3 different triangles. I then pieced together that this one's going down, and this one's going down, this one's going up, and this one's going up, and I made myself a formula, and I added and subtracted the vectors the right way to get a net amount right here at G. Then in X, I found this one and this one should be equivalent to this one and this one, and I found what H's momentum was. Once I found 2 sides of a triangle, I used Pythagoras' theorem to find the 3rd side, and I used an inverse tangent to find the other angle. Along the way, I must have had like at least 8 to 10 different numbers, right? Because there'd have been 1, 2, 3, 4, 5, 6, 7, 8 different numbers going on here that I have to use. So make sure you're meticulous in writing down all your work. Okay. One last thought, then I'll shut up so you guys can work on whatever you want. You can ask me questions then if you want. You can keep looking it over. You are not getting like 7 of these. Okay? You might get 1 of them. You may even get lucky on the diploma and you don't get this one. You get this one. Now, in theory, you can actually solve this using vectors as well. You could have broke this up into the momentum in the x direction, a momentum in x, a momentum in y, and then another triangle where there's momentum in x, momentum in y. You could even do that as well. But in this case right here, cosine law is almost always the best choice, and it's even on your formula sheet. Like, they give it to you on the formula sheet for a reason. So hope that you're going to get this one here, because this one's so much nicer than the other one. So, okay, I'll stop the recording here. For the last little bit of class here, what I'd recommend now is do some practice, okay? So try my assignment, call me over for some help, and then tomorrow we're going to use that little mini pool table up there. We're going to make some collisions. We're going to find some masses, velocities, distances, times. We're going to throw it into a computer program, and we're going to try to see in a very similar way whether or not the y momentum is the same, whether or not the x momentum is the same. Okay? And hopefully by doing it in a tangible way, that'll help as well. Sound good? Okay, rest of the class is yours until I guess we're to go. Ask me questions, okay? Now is a great time to.